This video is going to introduce you to the concept of derivatives. I'm going to show you what is called the definition of a derivative and how we're going to do derivatives using limits in the beginning. We're just going to do a brief video on this, and then we're going to get into shortcuts to doing this strategy called the differentiation rules. However, before we get to that, we have to go through the long way to find derivatives. Before I even get to that, I want to review with you how to do some function notation because it is part of the definition we're going to come up with here. So I want to refresh your memory on something that you've done. You've done it a couple of different courses now, or something like this. If I had f of x equals x squared minus 3x plus 2, and I said to you, find f at 3. Well, what that wants you to do is where there used to be x, replace it with a 3. So it looks like this. Wherever there's an x, you just put a bracket. And then you simply replace what's in the where the x was, you put this in there instead. So it'd be that, and then you could figure out what this equal to, which I'm not concerned about that. I want you to make sure you understand how function notation works. So again, using the same function, I'll use this as my f of x for all of these. If I said, okay, what would f at 0 mean? It doesn't change its meaning. It means go to function f, there's function f, where there used to be x, put 0 in its place. So it would be bracket squared minus 3 bracket. You replace the letter x with a 0, like so. And you can figure out the answer if you wanted to. I'm more concerned with the actual substitution at this point. All right, well, if I said, what if it's negative? F at negative 2. Do you do that any different? No, you do not do it any different. It's still wherever there used to be an x, you're now going to put negative 2 this time. And I think most people will agree that's not very difficult. Yeah, I remember doing that. No problem. Where students run into the issue is, and we did do a little bit of this in pre-calc 12a, is if I ask them something like f at 5w. Nothing changes. You still do it the same way. Wherever there used to be an x, here it was just a single number. Well, here you're going to put 5w wherever there used to be an x. Should be squared. So I just simply replace 5w in where the x used to be. So how do you know it goes where the x is? It's because this is where the x used to be in your function notation. So then, if we progress even a little bit further and say, well, what if I'm going to use, because in the definition of a derivative, we use a binomial. So what if I had something like this? F at 2 plus h. As I said, nothing changes. Where I used to be substituting x, I'm going to replace all the x's with now a binomial 2 plus h. So it would look like this. Bracket squared minus 3 bracket. Oh, so I'm making the bracket a little bit bigger because I know that I'm going to have to put 2 plus h in there. And then I simply replace the letter x with a 2 plus h. This one here I'm actually going to expand out because this is what we're going to run into in our definition. So we've got to make sure we're able to do this. Just refresh your memories and make sure you square binomials properly. Square the first, multiply, so 2h, and double, so that'd be plus 4h. Square that one. Still find students every once in a while in pre-calc 12 classes where they're just squaring this one, squaring this one. That is not how you square a binomial. 3 steps. Negative 3 times 2 would be negative 6. Negative 3 times h would be a negative 3h. And then a plus 2. Got a few like terms here, so I could collect, just the 1h squared, but I do have a negative 3h and a plus 4h. So those could be combined to give me plus h. And I've got a plus 4 and a plus 2. There's a simplified version of f at 2 plus h. Just do one more quick one. What if it was f at, I don't know, x minus 2h? So that wants me to put x subtract 2h everywhere there's an x. So it would be f at, sorry, not f at. I don't have enough room to squish it in over here, so I'm just going to put it underneath there. Would be wherever there's an x, replace it with a bracket, minus 3, bracket, plus 2, and this time I'm going to put x subtract 2h in the bracket, x subtract 2h, x subtract 2h, binomial squared, 3 steps. Square the first, multiply these two together, I get negative 2xh, double it, negative 4xh, square this one, you got to square the coefficient and the variable, so it would be plus 4h squared, negative 3 times x, negative 3 times a negative 2h, plus 6h, plus 2. I don't think we have any like terms this time, so there's nothing further I could do to collect terms together here, so that would be our final answer of f at x minus 2h. And that's the way you say it. You say f at 3, f at 0, f at negative 2, f at 5w, f at 2 plus h, f at x minus 2h. You know, sometimes that word will get replaced too by f of 5w, f of minus 2. Okay, so hopefully that shared your memories a little bit on function notation. And now we're going to get into the nuts and bolts of probably the most important thing you will study if you're going to take any kind of calculus courses. And it is what is known as a derivative. We're going to, just in this quick lesson I'm going to do today, we're going to go through how to do this using limits. However, we will not do derivatives using this strategy unless we're told to after the next video, because I'm going to show you a bunch of shortcuts that make it a lot easier to do this. Okay, so leading up to that, I'm just going to try and give you some context of what a derivative is. So there's kind of a written definition I grabbed off the internet here. It says the concept of the derivative is at the core of calculus and modern math. It can be approached in one of two ways. You can look at it as the slope of a curve or as a rate of change. But if you kind of examine these two things a little bit more carefully, slope and rate of change are really the same thing. When you did slope as an introductory thing back in probably grade 9 and 10, they often called rate of change slope before we ever used the word slope. So they're really the same thing. This is the formal definition of a derivative. I'm just going to leave that for a second, but don't write it down yet. There's another slide coming up where I kind of show you where this all comes from. There's a little symbol here now. It's a new symbol. It's called f prime. So the way you say that would be the word prime. It is a symbol, not prime, like John. It's prime. F prime of x. That is the notation that indicates to us they're looking for the derivative. Of course, at this point, you're saying derivative. What's all this derivative stuff he's talking about? Well, derivative is essentially the slope of a tangent that you would draw to some function. And the theory behind what we're going to do is we're going to take, so I've got a few diagrams down here. You're going to take, and this green line would not be a tangent, it would be a secant. But imagine that what we're trying to figure out, I'll draw a straight line here as best I can. I'll say I use this one. If I was to draw a tangent line at this point right here, point P, well, it would look something like that. I'm assuming you know what I mean by a tangent, so maybe I'll just bring this out here for a second. Here's an example of a tangent. Let's just twist this around a little bit better. A tangent to a graph is a line that just touches it. So I'm just going to pick a spot here, let's say right about there. Now it's hard to tell because of my line I've used is a pretty thick line, but by definition of a tangent, it's a line that just touches, the different color, touches a graph at some point, and that would be called the point of tangency. And this line here that just now can't, so that's not a tangent. It can't cut through the line. It can just touch it on the outside edge somewhere. So you could have a tangent. Again, I should put a different color. There's a tangent. There's a tangent. There's a tangent. That's not a very good one. That's more of a secant. You should just be trying to barely touch the function in one spot. There's a tangent. So I could draw tangents anywhere I want on this graph. Well, a derivative is us finding the slope of that line. The slope of a tangent is one of the definitions you saw up above. Now, sometimes students will, if we were in class, I kind of generate some discussion. I said, what do you know about tangents and slopes? Da, da, da. Well, one of the things that students say, oh, I know how to find slope. The slope of a line is the change in y, or the y value subtracted, and then you subtract the x values. And that is exactly how you find slope. But the problem is, to use that formula to calculate the slope of a line, you need to know 2 points on the line. The problem with a tangent line is often the only point we have is this one point called the point of tangency. So my formula that I traditionally would use in grade 10 to find the slope of a line will no longer work for me because I only have one ordered pair to use. So this traditional way won't work. Now, that doesn't mean it's not going to help us, because it is. You're going to see in a few moments that it's going to help us. Here's the theory behind what we're going to do. We're going to take, maybe let's see if I can draw this freehand. I'll take this over. If this was my tangent line, and I was going to draw it to the graph, the blue graph at the point F, I'm just going to twist it around a bit here, get it situated a little bit better. Up that up a little bit. So it would look something like that. Maybe I'll just twist it a bit more that way. Here's my point of tangency. Right there, that's that point P. So this line is just touching it, and I want to figure out the slope of that line. Well, here's the theory behind it. The theory behind it is you draw a secant instead. Because a secant, you'd have the point of tangency, so it goes through there, and then you get another point up here, and you find the slope of this line, right, the secant, and it becomes an estimate for the slope of the tangent. However, if I drew that point way over here and found the slope of this green line and said, well, for example, this has a slope of 2/5. Well, the slope of this secant, being, let's say, 2/5, is quite a poor approximation for the slope of this line, because you can see that it's nowhere near the slope of this line, because when they have different steepnesses, they have different slopes. Well, now just bear with me here. I don't know what's going to happen here. I'm going to take this point Q, and you'll see I got a bunch of slides overlaid on top of each other here, and I'm going to delete them. And every time I delete one, the point Q, I'm going to move it a little bit closer to this point. And you're going to notice, what you should notice, is that the secant is going to be slowly coming around as I draw it on here, and it's going to be getting closer to laying on top of the tangent line. So let me just look at what happens. So I'm going to probably have to delete my handwriting here in a second. I'll just try this. So I'm going to delete this one. So the secant, yeah, it's kind of moving on me a little bit here, so I'm just going to avoid confusion. Okay, so I'm going to leave my tangent is over here. So your secant, you can see even just by moving it from there where it was over to here, it's getting a whole lot better already. So if I found the slope of the secant using these two dots and my regular slope formula from grade 10, it'd be a lot better than the last one. Well, let's try to delete that one. Well, I'm going to delete even this big one now. We don't really need that. If you look at that secant, the line connecting, so Q is even closer now. It's over here. It started out way over here, and we put it kind of here somewhere, and then we put it now here. Well, that secant, if I just freehand on here, my tangent line, well, it's running pretty close to my secant. Well, the theory behind it, and if you want to get into the calculus of it here in a second, the theory behind this will be, as I get closer, so notice Q is even closer again. Now Q is even closer. Down here, I got one more. Those points now are really, really, really close together, P and Q. And if I was to take those two ordered pairs that you see here, P and Q, and put them into this formula, so let's suppose I knew the coordinates of those two ordered pairs, and I went into my old slope formula from grade 10, which was y2 minus y1 over x2 minus x1, and I found the slope of that. Well, that secant would be awfully close to the slope of the tangent, which I draw there. You can see that they're almost laying right on top of each other perfectly. So the theory behind it is, well, if you made that point as close as you possibly could to this original point and found the slope between the two dots, it's for all intents and purposes going to be the same as the slope of the tangent. And the slope of a tangent, anywhere you draw on a graph, is what we call, so the slope of a tangent is kind of a crude introductory definition of a derivative. That's what a derivative is. It's the slope of a tangent at any point you pick. Now, slope of a tangent is also called rate of change. So in this spot right here, if I pick that point, I could see that it's a line. If you look at it, it's pretty close to over 1 up 1. It almost looks like it has a slope of 1. The symbol I showed you earlier was f prime of x. That's the symbol that means derivative. There is another one I'll show you in a little bit, but that's kind of the most commonly used one, this one right here, f prime of x. Over here, if I drew a tangent, let's say, wherever, right there, that line definitely has slope that's negative. So f prime of x at that particular spot on the graph, right there, I don't know what it is, but for now, I know that it's negative. Over here, my derivative, or my slope, would be positive. Right at the very top here, if I draw a tangent, this would be a spot where slope would be 0, which is another way of saying f prime of x is equal to 0, and that symbol, f prime of x, I know it's new to you, so it's a little awkward right now, but you'll get used to seeing and hearing it over the next little bit. That's the symbol for the derivative. This is telling me that the derivative, or the rate of change, or the slope of the function at that particular one spot right there is 0. And you say, well, how'd you know that? Because it's a horizontal line. And from grade 10, when you studied slopes of lines, horizontal lines always have a slope of 0. This is kind of the background geometry of where this all evolved from. So I'm going to show you now where that formula that you saw up here, I'll just scroll up for a second, which probably looks kind of obscure right now. I'm hopefully going to clear up where this came from. Okay, so I'm going to go back to a situation. I'm trying to find the slope of this red, pink colored line here, the tangent. I'm going to use the blue line to do so. The theory behind it is you pick this point, your tangent point, and it is some ordered pair, x, comma, y. Well, then you've got this other point up here, which is, so this point is drawn at x. You take this point and you put it here and you move over slightly. So we call this point x plus h, where h is the distance between the 2 points. Okay, so if I take this point and fill it into the function, I'll get an ordered pair. Now this is where function notation comes in. So this ordered pair right here would be the x value, x plus h, and the y value, the way you get the y value is you fill the x value into the function. So it would be f, the function, whatever it is, evaluate it at x plus h. That's the y value at that x value. If I go back to this one, rather than putting a y here, I could say this is the ordered pair x. And you say, well, how do you get the y value? You fill x into the function, whatever it is. I've now got 2 points. And I'm going to find the slope of this blue line. So this is my secant. So my secant is found using 2 points. That's a secant. I didn't define it, but it's a line that cuts the graph in 2 spots, like this one. So the slope of a secant is your regular slope formula. I'll just put it up here so you can remember y2 minus y1, x2 minus x1, nerve 10, slope formula. Well, the y value here is f of x plus h. Minus, and h is just how far you're going to move over here. We'll get back to that in a minute. The y value at the other point down here is, instead of putting the letter y, I'm just going to say it's the function evaluated at that x value. So it's f of x. That's your two y values subtracted. Now it's y2, which was x plus h, sorry, x2. That's the x value up here. Take away the x value at this ordered pair, which would just be x. Okay, so that blue line is going to have a slope of f at x plus h. Take away or subtract f of x, and the denominator is going to clean up and just be an h left down there. All right, so that's how you get the slope of the blue line. But that's not what I want. I don't want the slope of the blue line. I want the slope of this reddish colored line right here. So the theory behind it is, I tried to show you on the last ones, is we picked this point and I've drawn it in such a way so we can clearly see it. But this blue line is not a good approximation for the slope of this red line. So I would then, if we were in class, I'd kind of try and prod you folks to give me some answers. I'd say, well, how can I make that better? Well, the way you can make that better is move this point so it's not so far away. Why don't you put it right here? So let's say instead of it being drawn way over there, put your point, let's say right there. It's still going to be called x plus h. The difference now is that h got a lot smaller. H was originally this far apart. That's how far apart the 2 points were. So now h is only this distance. And if I was to draw a line between this green dot and this black dot here, well, you can see that that's getting pretty close to now, or it's a lot better than the blue one for sure, to, in terms of checking the slope of the green line compared to this one, it wouldn't be very far off. So then I'd say, okay, well, how do I make it even better? Put this even closer. Now, this is where limits comes into play, which you just get done studying. I would like h, the distance between the 2 points, I want that point to keep moving this way, closer and closer and closer to x. Now you can't put it right on top of x because then it's 1 point. So it's got to be ever so slightly to the right of x. Well, what I want then is the distance between these two to approach 0. And this is where, as I said, limits comes in that definition. So this is now what is referred to as the slope of a tangent, which by definition is what's called the definition of a derivative. So I've kind of looked through over the years a lot of introductory calculus, old exams and midterms, and almost every single one of them, somewhere on there, will say using the definition of a derivative, differentiate is the verb telling you to find the derivative. So differentiate the following function. And I'll show you some examples of that here in a moment. So here's the definition of a derivative. It is this formula right here. Slope of a secant. F at x plus h, subtract f at x, all divided by h. Now keep in mind what h is. H is how far apart these 2 points are. That's the formula for the slope of a secant. But a derivative is the slope of a tangent. This little notation in the beginning turns it into a tangent. Find the limit of this function as h approaches 0. Meaning, as the distance, because h is how far apart the 2 points are. So let's say this one is started out and say, oh my goodness, they were 1.2 units away. Then down here, oh, they're only 0.2 units away. Well, I want them to get even closer. So what I want is h, the distance between them, to approach 0. Now, that can be confusing and hard to kind of get your brain wrapped around even while you're sitting in the classroom. So I can imagine while you're sitting watching this video, you may be saying, oh my goodness, this is just going to get chaos. Here's the bottom line. You need to know this formula right here. You got to study it, got to know it. Good news is this year, there's no exam or anything, so truth be told, You'll be sitting at home doing any of your work. You'll be able to look it up if you have to. But next year, if you take calculus, you're going to need to know this formula. How it came, where it evolved. It's nice to know some of the background work, like I tried to explain here as best I could on this video. Um, Bottom line is, this is what you need to know right here. The definition of a derivative. The symbol, if you see in a question, find f prime of x, that is the symbol that means find the derivative. And that is what this is. This is the definition of a derivative. You'll see, I've seen some, usually I find the older textbooks, but I've seen this also called the first principle of calculus. So if you ever see an example that says using first principle of calculus, it's another way of describing the definition of a derivative. I've also seen it called the limit definition of a derivative. So if it says evaluate the following derivative using limit definition, this is what they're talking about. Limit definition of a derivative. Okay, so have this jotted down somewhere on the page in front of you so that moving forward, as I start using, so I'm going to show you now how to use this to get a derivative. And this is just basically the same. This is just saying f prime, so that's the notation for a derivative. Instead of an x, I'm using a. So that's just meaning I pick some number. So if I write out here f prime at 3, I would hope that eventually, and again, I get it, this is not easy to try and get your brain wrapped around sitting at home watching this on a video. This means the derivative of function f of x evaluated, meaning I want to figure out what it's actually equal to, evaluated at x equals 3. So then if you kind of even break that down to more basic, say, well, derivative, what's derivative? Oh, wait a second. He told us that derivative is the slope of a tangent. So f prime at 3, I can translate that into meaning go to your function and find the slope of a tangent drawn to that graph at the x value 3. That's what this translates to mean. Slope of a tangent drawn at x equals 3. That's a basic definition of a derivative. Slope of a tangent at x equals 3. So if I wrote f prime at -2, that would mean go to the function f, find its derivative, use that to figure out the slope of a tangent at the x value -3. This is telling you where you're going to draw your tangent line. That's why they're just putting here a. Now, we did it just generically for any x, which is how we're going to do these out. We're going to just do them for x, and then if they want this, we'll fill it in at the very end. This is showing you could fill the number in at the beginning if you want it. Again, I don't usually do it that way, but I'd like you to see it. I don't think I'll even go through that definition this year. If I had more time in class, I probably would, but doing the way we are this semester, I think we'll kind of skip over that one. So we're just going to rely on this definition right here. The other note, so I already talked about this notation. The other notation that they use for derivatives, it's called Leibniz notation. So this one is your f prime of x. That means find the derivative at x. This is another symbol. As I said, it is called Leibniz, L-E-I-B-N-I-Z notation. The way you say it is dy over dx. Now, I want you to say, if we were in class, as I said, we would kind of discuss, do you think there's any reason that it looks like this? And often I'll say, what about slope? Students say, oh, slope. Oh yeah, that's derivatives, are slopes. Well, I want you to think of when you were first introduced to slope, it probably looked like this. Delta, triangle. So triangle, delta y, divided by delta x. D, delta, delta. As I always tell students, I wasn't there when they come up with this notation. However, I'm going to kind of guess, make an educated guess. The reason it's dy over dx is because derivatives represent slopes, and slopes are represented by a change in y over a change in x. The Greek symbol, this triangle is a Greek symbol for delta, delta y over delta x. So that is where they come up with that notation, dy over dx. So if you see that symbol, it means the exact same as this. They are interchangeable. This means find the derivative of the function just like you normally would here. Okay, let's put this all to work here. All right, here's example one. Using the definition of a derivative, differentiate the following. Well, first thing I'm going to do, and I suggest you do in any question, because you don't know the definition, the more you write it out, the more likely you're going to be to remember. So start every question by writing out the definition. There's the definition of a derivative. What I personally like to do is my f of x plus h. If it's going to be something that's going to involve a little bit of work, is I'd like to kind of just go over here in the margin and I figure out what is f of x plus h. Now this goes back to show you why did I do that little review on slide 1 before I even get into the definition of a derivative. I'm going to put x plus h in wherever there's an x. Now I'm going to expand it, and the reason I'm doing it over here is because I don't want to have to keep writing this out over and over as I'm doing all the expanding of this. So I'm just going to expand it all out, and then once I have it expanded out, I'm going to replace f of x plus h with whatever I get here. Square the first, multiply and double, square the last term, take away 5x, take away 5h plus 2. No like terms. So that's already simplified as far as it'll go. All right, I'm going to go to my definition. I'm going to try to color code things here. So limit as h goes to 0. That's staying the way it is. That's going to be written the whole way down. F of x plus h. I just did the work for it. So that expression right here, f of x plus h, I'm going to replace with all of this stuff because that, look at what it says. F of x plus h is equal to this. So I'm going to replace f of x plus h with what it's equal to. I'm going to put it in brackets. Not that it really matters in this one, but it will here in a second. So plus h squared minus 5x minus 5h plus 2. There's f of x plus h. And then I'm going to subtract f of x. So what's f of x? Well, just if you look around, it says here y equals. Y equals is another symbol that's the same thing as f of x equals. So f of x is always just your original function. So in this case, that original function, this is the one that's really important. It goes in brackets. X squared, subtract 5x plus 2. So that's always your original function. And again, it might not say f of x, it might be g of x, it might be h of x, it might be y equals. This is kind of interchangeable for generically the original function. Now, do you see why these brackets are so important? Because if I don't put those in brackets, this negative, the way it's written now, this negative is going to go here, and then it's going to distribute here, and then it's going to distribute here, and that's what should happen. If I don't put those brackets, that negative's only going to go here. These are both going to have the wrong sign on them. So this one is really, really important that it's in brackets. As I said, this one, it's a little bit less important, but I find it kind of shows you your formula. So there's your f of x plus h. There's your f of x. Now you've still got your h down here. Now, knowing what's supposed to happen will help you moving forward. Here's what's supposed to happen. Anything that doesn't have an h in it should end up crossing each other out. And if that doesn't happen, something's gone wrong. This is what I mean by that. See how I've got this x squared? There's no h on it anywhere associated with that. But there's an x squared over here as well. So this x squared is going to subtract x squared. They're going to wipe each other out. I have a negative 5x here. This negative, when it goes in here, is going to make that into a plus 5x. Well, if I had a negative 5x and a plus 5x, they're going to wipe each other out. I have a plus 2 This minus is going to go in here and make this a -2. Those two are going to wipe each other out. And notice the three that are left. This is what I mean. See how they all have an h factor in them? That's what should happen. If that does not happen, something went wrong. Either you expanded this wrong, you didn't distribute your negatives, but everything that doesn't have an h on it should cross out from the numerator. Now, there could be more stuff down here eventually, depending on the type of function, but up here, this is all going to cross out except ones that have h's on them. Then watch what we do. We factor. We take out that GCF of h. So I take out h. I'm going to get 2x plus h minus 5. And then I'm going to have an h here. I should back up one little step here. The problem is this limit, if I had tried to put h in right now, anything that had an h in it would have became 0. These would have all crossed each other out. So you would have definitely got 0 on the top. And obviously the bottom is always just a 0. So this definition with h going to 0, you got to get rid of that h in the denominator somehow. And what should always happen is you'll end up, that's why you want to have this factor of h. You factor it out, and then you know you're in business because perfect. There's your problem fixed. Now you can make h become 0. Here's h, right? That says here h is going to 0. And by making that go to 0 now, because these are crossed out, that's no problem. And you're now ready to write out what is called the derivative. So I'm going to use, so because it's y, I'll write it as y prime. The derivative would be 2x minus 5. That's the derivative of this function. This process we're doing, it's called differentiation. So if the instructions say differentiate the following, see right up there, differentiate each of the following. That's what I did. I used definition of a derivative to differentiate or find the derivative of this function. And again, you have to have patience. I know this may all sound kind of obscure at this point. It's just a comfort thing. You'll get comfortable with it. You'll get used to it. It'll be just everyday lingo we'll use as we get going here with differentiation and derivatives. So then you said, well, what the heck would I do with that? What is that? What I could now do is say, what if I drew a tangent? A tangent at, let's say, x is 3. Well, you know what? I could go here, y prime. I could fill in x is 3, right, for the x. And I get an answer of 1. That's what I say. So what? What is that? This is what I want you to understand. This is why I kind of went through the whole tangents and all that kind of stuff. This would be the slope of a tangent drawn to, in this case, the original function. I'll just go up and write it down here. So whatever this looked like, x squared minus 5x plus 2. X squared minus 5x plus 2. Slope of a tangent drawn to that graph at the x value 3. That line would have a slope of positive 1 if we drew it. And you could pick another. Pick x is 4. 2 times 4 is 8. 8 minus 5 is 3. That means if x is 4 and you draw a tangent line to this function, whatever it looks like, then that line has a slope of whatever the derivative is at that point. So in this case, we said it would be what? 3. 2 times 4 is 8 minus 5 is 3. That's if I picked x as 4. You can just keep putting different x values in there. You'll get different slopes of tangent lines. All right, on we go. Here's another one. So this one's got a radical in it. So I picked out 3 of the common types. So the first one's your polynomial. The next one here involves a radical. And nothing changes. You use the definition, limit of f at x plus h, subtract f of x, all of that divided by h as h is approaching 0. So to do that, I need to figure out f at x plus h. This is f of x, so that's going here. This part, that's f of x, that's here. F at x plus h. On this one, I could probably do it on the fly, but we'll write it out over here. It's the square root of 2. You replace x with x plus h, which is going to give me 2x plus 2h minus 5. That expression is equal to f at x plus h. So that's going in here for this. Limit of square root 2x plus 2h minus 5 minus square root, so f of x, says right here, look, f of x is this, 2x minus 5, all of that over h as h goes to 0. Well, the good news is we've already studied limits. Last unit, I guess we'll call it. Bad news, you need to remember all that stuff that we did last unit. So you need to remember your strategies for evaluating limits. So when I look at this one, if h went to 0, I'd get the square root of 2x minus 5 minus the square root of 2x minus 5, which would be 0. H becoming 0 would be 0. It's going to be 0 over 0. Every single time you use the definition of a derivative, you're going to generate an indeterminate limit. It's always 0 over 0. You're then going to have to use your skills that you've developed on limits to proceed and get rid of that indeterminate form. Well, in this one, we're going to rely upon the strategy we used last unit when we had two radicals or a single radical called rationalizing. We're going to multiply the numerator and denominator by the conjugate. 2x plus 2h minus 5. So the conjugate, you just switch the sign between the two radicals. That's all that changes. No other sign changes. And then you multiply the bottom by the same thing. 2x plus 2h, 3 minus 5. 2x plus 2h minus 5 plus square root 2x minus 5. That is, we know, is called the conjugate. And what we're doing is called rationalizing. Okay, so if you're rationalizing the numerator, you're going to expand it out. Because they're conjugates, all you got to do is multiply this by this. Well, here's the good news. This radical and this radical are always going to be identical. So when you multiply the two together, it just gets rid of the square root sign. So h is still going to 0. So you're going to get 2x plus 2h minus 5. Minus, because it's a positive and a negative, and they're conjugates, the middle terms are going to give me 0. All I then do is multiply the two last ones. Well, they're the same thing. It's going to get rid of the radical. So that gets that cleaned up a little bit. The bottom, just leave it like it is. So you got your h multiplied by this stuff, just put it in brackets beside it. Square root 2x plus 2h minus 5 plus square root 2x minus 5. Now, like the last one, anticipate what is supposed to happen so that if it doesn't, you can figure out what went wrong. Here's what should happen now. The numerator, because this h has got to cross out. If h is going to 0 and that's still down there, the bottom's going to be 0. That has to cross out. Let's look at what happens in the numerator. 2x minus 2x. Those are gone. I've got a negative 5. This negative distributes in here and switches this to a plus 5. A negative 5 and a plus 5, they wipe each other out. Like the last one, look at there's only one single term left. It's got a 2h on it. And what's the nice thing about that is it has a factor of h. So we're going to write that out one more time. And we'll do our dividing here. So limit as h goes to 0. So all that's left in the numerator is 2h. Everything else crossed each other out. Then you have an h here. Bracket, leave this alone. 2x plus 2h minus 5. Square root 2x minus 5. Line goes all the way across. This is 2 times h. This is a factor h. You can cross those out, divide them out. Now, sometimes students say, oh, it's 2h minus h. No, it's dividing. This h divides this h out, and they're gone. Here's your final answer. So h is now going to go to 0 without any issues because this is gone. So all you're left with so I'm going to go to my notation now for derivative. F prime of x will equal. In the numerator, when that h crosses out, all that's left is a 2. This is gone from the bottom. That's good. This 2h, h is going to 0 still. So that's going to become 0. You're going to get the square root of 2x minus 5 plus, there's no h in this one, so that's just going to stay, square root of 2x minus 5. Well, in this one, if you have two radical, why do I have a plus? This one should be minus 5, sorry. It should be exactly the same. So here, if I go minus 5, I have two radicals that are identical added together, so I should be able to collect those. So it's 2 radical 2x minus 5s. And then if you want to simplify even further, you can cross those out, and you get 1 over the square root of 2x minus 5. That is the function that will give you the slope of a tangent at any x values of that function. All right, so that involves the radicals. And again, I understand you may have to pause, go back, watch this again. To sit and just watch this nonstop one time through is probably going to be a challenge. Okay, I got one more I want to show you, and this involves rational expressions, so a fraction. This has a little bit extra to it. It says find f prime at -1. All that means is once we get the answer, we're going to put -1 in for the x. So everything's done the same to begin with. So let's get it started the way we did the last ones. Definition, limit f of x plus h, subtract f of x, all divided by h, as h is approaching 0. Do not get lazy. Use proper notation. Again, I can't be there to watch over you, but if you were in class, I'd be harping on you to make sure you use proper notation. Students are lazy. They don't want to write this out. It needs to be there. Okay, so f of x plus h, I'll just put it over here. F of x plus h. I'm just going to simply replace x with x plus h. Well, there's not much else I can do with that, so it's ready to go. So there's what I'm going to put in for this. Limit as h goes to 0. F of x plus h is this fraction. 4 over x plus h minus 5. Minus f of x, that's the original function. 4 over x minus 5. And it's always over h. Well, again, as always, if you were to put h as 0 right now, you get 4 over x minus 5, take away 4 over x minus 5. That's 0, and the bottom will be 0. So as I told you last example, it's always 0 over 0. So at this point, you need to be competent at evaluating indeterminate limits, which was one of the main focal points last unit. Well, we did this last unit. When you have fractions within a bigger fraction, our strategy was find common denominators. So I'm going to take those two fractions in the numerator, x plus h minus 5, and x minus 5 are my denominators. So your common denominator is the product of those two. The first fraction, if it's right now it's over this one only, but I want it to be over this times this, which means the numerator would have to get multiplied by x subtract 5. The second one is over x minus 5, but I want it to be over these two multiplied together. So I have to multiply it by x plus h minus 5. So this is these two fractions in the numerator combined with a single common denominator. Instead of putting it over h divided by h, remember, dividing by h is the same thing as multiplying by the reciprocal, which would be 1 over h. So what I do, just instead of putting it back over h, I just put times 1 over h out beside it. That's the same thing as dividing by h. Well, if you're starting to get the drift of this at all, you're probably guessing what should happen here. What should happen here is we end up with some h that's going to cross out this h. So let's see if we expand the top out of this fraction. 4x, take away 20, take away 4x, subtract 4h plus 20. That's the numerator. You still get this, so that doesn't go anywhere. X plus h minus 5, x take away 5, multiplied by 1 over h. So room here. Well, let's see how this worked out. Anticipate what should happen. Everything should cross out except the ones with h's in them. 4x, take away 4x. Beautiful. Negative 20 plus 20. Wonderful. The only thing left is negative 4h. So let's limit as h goes to 0. Negative 4h. Nothing happened in the bottom. It's all still the same. I've got my multiplied by 1 over h. Look at that. H, cross each other out because they're factors. You're allowed to cross out factors. You couldn't cross them out here because that's a term. So you have to expand it all out, get everything to cross out except that single term with the h. Now you got your factor h, it's gone. I'm going to now write this as f prime of x. And remember, h is going to 0. So that means this term right here, because h is going to 0, is going to become a 0. It doesn't affect anything. I don't get 0 over 0 anymore by that happening. So here's what's going to be left. Negative 4 in the top. That's all that's left across the numerators. This became 0, so now I have x take away 5. And I've got another x take away 5 right beside it. Well, why don't we write that as negative 4 over x take away 5 squared. Beautiful. We did the derivative. However, this one had that extra step I showed you. It says, what's f prime at negative 1? So what it wants us to do, after we get to here, let's go this last little step, switch to a different color, f prime at negative 1 means find the derivative. Once you get the answer, put negative 1 in where the x is. All right, no problem. Negative 4, where the x is, put negative 1. And let's see, we get negative 4. This will be a negative 6, but I'm going to square it, so that'll be 36. Reduce that to negative 1 over 9. That would be the slope of a tangent if I drew it to f of x at the ordered pair, not the ordered pair, at the x value that I filled in here, negative 1. That's what derivatives are, slopes of tangents. So as I said, I picked out the 3 major different types of examples. So if you're doing some practice questions and you see one with a fraction, you get stuck, come and refer to this one. If you run into one that involves a radical, square root, come and have a look at this one. If you get into one with terms added and subtracted, we call that a polynomial, come and refer to this one. It's usually 99.9% of the time one of these 3 types that you're going to run into. I have put some practice questions in your class notebooks. So if you go to the I have to double check. They're either in the derivative section or the limit section. I can't remember where I put them. Anyway, they're in there under handouts. And it's just a few questions with the answers written right below the question. And you could pick a few of them and try them out using definition of a derivative. So you can see, any of you that tried taking shortcuts with limits, you're in trouble because now you're stuck here and you don't know how to do limits. You can't do this if you don't know how to evaluate limits. So that's where you get into that whole climbing the ladder deal. You can't start at the bottom and jump to step 5 on a ladder. You got to climb your way up. The same in this course. You got to climb your way up, do all the work to lead up to where we eventually end up. Okay, so not sure if we'll get an assignment on just this because I may give you just 1 or 2 quick questions, but then we're probably going to look at our rules of differentiation coming next. All right, good luck as always. If you have questions, reach out and ask sooner rather than later. Okay, sometimes students are waiting too long. I'm getting questions 5 minutes before an assignment's due or half hour after an assignment's due. That's no good. You have to ask questions in advance so you can get things cleared up and then you can do your assignments to demonstrate you understand the concept. All right, take care.